In this series, we're going to be looking at Math 1110 flipped classroom video lessons, and we're going to start off with topic 1.1, which is real numbers and algebraic expressions. This is sort of a review of your basic algebra course. I'm not going to go through these in detail at this time, but these are the objectives. You can pause and read them if you like. Now, to start your notes, you're going to write real numbers and algebraic expressions, and then we're going to go through the sets of numbers here, and you'll want to write out and take examples of what we're showing you as we go over this. To start us off, the first set of numbers in the real number system are the natural or counting numbers, and would include the symbol n equals, and then you're going to use braces and list them, and this 3 dots is the ellipses. And the ellipsis relates to the pattern that, starting off here, develops and then continues on. And then we can close it with another brace. And you might say, where is this going to? Well, this is going to what is called positive infinity. Now, the next set of numbers are whole numbers. And again, there's the title of the set. And the only difference between natural or counting numbers and whole numbers is we've added a 0. So again, use your brace, put the examples, create a pattern, and then conclude with the ellipsis. And this also goes to positive infinity. Next set of numbers are the integers. Now, if we have our whole numbers, which includes 0, and their opposites, that is what we would add to a 1 to make it a 0, the -1, and the -2, and the -3, and so on, and this would include integers. Now, for the symbol for integers, you may not see that too well. It's sort of a Z with a thickened central portion here. Integers. Now, in putting it in this notation, and by the way, let's add this word to it, roster notation. That is, you start with a brace. Now, the ellipsis is on the left end, and you might say, where is this coming from, or where is it going to? On this end, it's negative infinity, and on this end again, positive infinity. And these are the sets of integers. And again, you want to include that in your notes. Now, the next set of numbers are the rational numbers. Rational numbers, by definition, is when we have and we use the symbol Q for the rational numbers, is dividing a number, let's say P, by a valid number Q, gives you, and this would typically be referred to as fractions, make up, along with the integers, whole numbers, and counting numbers, are rational numbers. Now I'm going to go to the white screen to show you one other thing here. in just a moment. Now, if we were to graph natural numbers on the number line, it would look like this. And what we would do is, have them numbered 1, 2, 3, 4, -1, -2, -3, -4. This is the number line. So to graph natural numbers, we just put dots at 1, 2, 3, 4. These would be the natural or counting numbers. To make them whole numbers, we add a dot here. This is now graphing the set of whole numbers. Now to graph integers, we do the opposites of the whole numbers. And usually to indicate that it goes on, we thicken the arrow, or we sometimes use the ellipsis. Now, to indicate the fractions, that is, the numbers between them that are rational numbers, let's start with a real easy one right about there. This is 1/2. And in its decimal form is 0.5, and it terminates. Another number, and I'll change colors here. Let's use black. About right there is the number 1/3. Now in its decimal form, it's 0.3, and the threes keep repeating. We usually put a repeating bar over it to indicate that. So to summarize where we are at this point, numbers that are in fractional form that repeat or terminate, as we see here, are, along with all the other sets we've talked about, are the rational numbers. Now, going on to our last little set, suppose we are at a number right about there on the number line, which is the square root of 2. Now, the square root of 2 in its fractional form is 1.414, and it just continues without a pattern, and it doesn't terminate. Another famous one is right about there, which is pi, and that is 3.14, and that continues on and doesn't terminate or have a repeating pattern. Another famous one that we'll use later in the course is the letter E, which is about 2.718, as I recall, and it doesn't repeat a pattern or terminate. These make up the other group of sets of numbers, of real numbers, called irrational numbers. All right, now let's see that. I wanted you to see how they fit on the number line. And everything on the number line, all the numbers, are called real numbers. All right, let's go back to our other screen. And here we see them, the irrationals and the real numbers. So hopefully you have some good notes as background for the number system. So in summary then, the set of numbers we use primarily in this course, real numbers, starting off with the natural numbers here, whole numbers, integers, rational and irrational numbers with the properties we've mentioned. Now we'll include these example numbers in our notes. So you're going to call this example 1, and you're going to write this. And what they're asking you to do here is to pick out from this list of numbers the natural numbers. So for letter A, looking through the list here, now the square root of 9, the square root sign is an operation, so it's to take the square root of 9. This will be a 3. So the first one that's a natural number is the 3, sort of disguised as the square root of 9. And then 10, the 17th power, that would also be a natural number. Now to get to whole numbers, all we'd have to do is add the 0. To get to integers, we would add the negative 15. These are fractions, and this one is irrational. Now the rational numbers for letter D, everything we've had so far, but now we can add our fractions, a negative 7.5 and a 1.6 with the repeating bar, and then everything else we've added. And now, what would be the irrational numbers that we'll see down below here a little bit? Well, we have the square root of 2. That's going to be letter E here, and pi. Okay. And we see that at the bottom. Now, we showed the number line in an earlier part. Notice the positioning of it. There's 0. 0 is often referred to as the origin. And a little bit of history is, early man, caveman or whatever, they did counting numbers pretty well, but they didn't know of negative numbers. Negative numbers had to be invented. That was at a later date. Now for number 2, or example 2, you want to write that down. Part A is to draw a number line and then put these on it. Part B, draw a number line and again put these on it. You want to have a skill of knowing what to do. Now later you'll be doing your practice and certify, where these skills will be important. And of course you can pause as needed. Now for some background information, and often I like to think of this using the words background in your notes. And you want to write these symbols. A is less than B. A is less than or equal to B. B is greater than A. B is greater or equal to A. And generally, on a number line, the protocol would be anything to the left of something is less than anything to the right. And in a like way, anything to the right of something is greater than anything to the left. All right. Example 3. A. 5 is less than or equal to 9, since 5 lies to the left of 9. Now, in something like this is true, where the inequality sign is greater or equal or less than equal. If part of it is true, then it's true. So in B, we see 5 is less than or equal to 5. This is one of the rules. This is true. Now, a negative 7 is greater than a negative 163. Again, if you put this on a number line, a negative 7 is over here, and way over there is a negative 163. The statement 5 is greater than negative 2 can be written 5 is greater, using the symbol negative 2. We're just copying these down here. Letter E. The statement A is less than or equal to B plus C. Again, we can substitute here less than or equal with this symbol. The statement X is strictly less than Y can be written X is less than Y. Again, we're reviewing terminology, so we're all on the same page. Now, the negation of a statement, this is kind of interesting. That if we say A is less than or equal to B, to negate that, to make it the opposite, we would say that A is greater than B. You would not use the greater and equal or equal, because here this is A equals B. So this is sort of a unique thing you need to note. And then our last, A is less than or equal to B, and A is greater or equal to B. In this case, A must equal B. Okay, that's kind of an interesting verbiage there. All right, let's go on. For more background information, we're now going to take a look at what is called set builder notation, and then in a few moments, interval notation. Now, in mathematics, there are certain ways to write things, and set builder notation is written like this, where you use a brace. X, the item you're thinking of, is such that, that's that vertical line, X has the property of R or P or whatever property you want to define. In example 4 now, we're going to take a look at item A, where they're giving us an example of X is such that X is an even integer. Well, another way of writing that, as you recall from our set notation, is roster notation, as we illustrate here. We could also describe this next one as 2n is such that n is an integer, since every integer in this case would be a multiple of 2. In letter B, X is such that X is an integer, again defining which set of numbers we're referring to, and negative 3 is less than or equal to X is less than 2. Now, if we were to put that in roster notation, it would look like this. So again, you want to tie in what the example is like as it compares to set builder notation. Continuing with an example of an empty set as background information. What is an empty set? Well, it would be a set that don't contain anything. And the way to write this is we can call it, and this is one of your key words, an empty set. A synonym would be a null set. And symbolism, we have a circle with a slash through it. that would indicate an empty set, or braces with nothing inside. Now, don't put a 0 inside here, because then that element would contain a 0, that set. So let's go on. And they're going to say, what would be another example in set builder notation? Y is such that Y is greater than 1, and Y is less than or equal to -4. Well, you see there are no elements in this set because there wouldn't be any values that would meet this definition. All right, let's go on. We're moving on to interval notation. For background, I would suggest you pause and copy as much of this as you can and write these keywords: interval notation, set builder notation, and you can take shortened notes on this, but under interval notation, you want to indicate the set, and these are indicated by parentheses, A, comma, B, and in set builder notation, X is such that A is less than X and X is less than B. So it would be all real numbers between A and B. Now, in this case, the value for A would not be included, and the value for B would not be included. Now, if we use brackets here, the A and the B, similar to the above, but now are included in the set. And in this case, we have a parenthesis and then a bracket. So in interval or set builder notation would be X is such that A is less than X, but X now is less than or equal to B. I don't know if you're picking up on this, is that when you use a parenthesis in interval notation, the item next to the parenthesis is not included, while if you use a bracket, the item is included. Now, another one that we need to look at is where we have two sets of parentheses, or a set of parentheses, and you have the negative infinity symbol. Now, infinity, whether it's negative or positive, is always with a parenthesis because we don't know where that value is, and it just never ends. Remember, infinity is a concept. Things go on to that point and just continue going on. Now, in set builder notation would be indicated by this. X is such that X is less than B. So there's our B value in a sense where it ends, but that B value is not included in the set because of the parenthesis. And we're using the parenthesis to indicate negative infinity. And then here's a case where we're using a bracket where our value for A is included. So X is such that X is greater or equal to A. Now, another item of vocabulary and symbolism, when we have something like a parenthesis and a bracket, we say that interval notation is half open, or in a sense, half closed. Half because part of it is defined by being equal to some value there. The parenthesis indicating that is not included. Now, two brackets would indicate a closed interval because you're defining the specific end and the beginning to something. And both of those items are included in the set. Okay, again, a short treatment of this. And I know it's a little tedious, but for background information. So for example 5, the interval, and this would be an open set in interval notation, represented by this in set builder notation. So x is such that x2 is less than x is less than 8. Again, the 2 and the 8 would not be included because of the parentheses. Item B, the interval where you have brackets on both sides indicates that it will start at -5, and -5 is included. Goes up to -1, and -1 is included. And in set builder notation would be written as this. Item 3, the interval, again, because of the bracket, -3 is included, but 10 is not. So notice the inequality sign we use there. And you're taking a moment to write this down. Now letter D, the interval, which would be open, starts at 4 but not including 4, and goes to positive infinity, and in set builder notation would be written like so. Now here's one that's particularly interesting, and that is where it's from negative infinity, comma, to positive infinity. So it would be open, and it would go through all real numbers. That would be, in a sense, if you were to graph it, would be a number line that's completely filled in. That would be the graphic illustration of this interval notation. For one lesson, this is quite an extensive review of background algebra items. And then here we're going to go to the Venn diagram and some basic set operations. Now there's a couple of key words here that we're going to look at, and we'll look at the Venn diagram below. And we can sketch this and just go over some things here. So if we sketch a Venn diagram, we use usually a rectangular outer configuration, and then put a circle for a set, and let's say another circle. And notice that the circle is intersecting. Well, we often describe these sets by using capital letters. Let's say this would be set A, and this would be set B. And this is within a universe of things we're talking about. We often use the symbol U for the universe. And then members of the sets. So for instance, this might have a number 1, 2, let's put the 3 there, 4, and 5. So what are the elements? And we use a funny shaped C with like a little line in the middle. The symbol is red, is an element of. So 1, 2, and 3 are elements of set A. 3, 4, and 5 are elements of set B. Now we're seeing also what is called here intersection. And intersection, we use the upside down U in a sense to indicate what is intersecting in these two sets. Well, that would be item or element 3. Another symbol they're introducing here is union, which looks like a U. And here the union of these two sets would be all of the elements. 1, 2, 3, 4, 5. And generally we put that in roster notation. And that's what they're describing here. So a shortened view and review of this. Sometimes shading of the sets are used. In this case, the diagram indicates intersection, and that is shaded. And again, review, the symbol for intersection is the upside down U as we see here. And if you wanted union, the shading would be all of these. All right. Now, as you do your practice and certification, you'll be asked to do things like this. So looking at example 6, there is a symbolism that's used. So we need to pick out union here. And the lowest number is -2, but that's not included. So we'd use a parenthesis. And then you would go to the highest value, which is a 9. And 9 is included. So it would look like that in union. Now, an intersection, where would the values in a sense overlap? Well, they would overlap at 0 and would only go up to 4. And because 0 is included in the set, we would have a bracket there, and 4 is with a bracket also, so that would be the result. Now, as we look at C, we're looking for intersection. And as we look at the numbers, there are no values for that. So that is an empty set. And for D, and one of the things we would do in other classes is actually graph that. So let's graph that together. It's coming from -infinity up to 4. So that would be a bracket, and it would look like so. And then this one's coming from a -1 and going in this direction. So since it's union, all real numbers then are involved, and the symbolism for that is this. Okay. In example 7 now, I've shortened it a little bit. So they're asked to simplify the following sets. So here we see set 1, 2. That's an interval notation or a set notation. These are braces here. And in union. So we would just list the elements that are listed there. Again, set notation. Now here, again, we're looking for intersection. And the one that's found in both is just the X. Now here you had to be familiar from an earlier part of this lesson, the Z. Those are the integers. And the R, real numbers. So the union of that would be, since integers are within real numbers, would just be all real numbers. Now here, intersection of integers with real numbers. Again, the members that intersect would just be the integers. And this is explained down below as well. Another background item is absolute value. Now, we write absolute value of something by using vertical lines to either side of something. And we say the value of this, and the way they defined it is its distance from 0. Now, here's where 0 is, and let's say there's a 2, and there's a negative 2. Now, the distance that something is from 0 is always going to be a positive value. So this is 2 units from 0. It's negative value. And the positive is also 2 units from 0. So we generally say the absolute value of something is always going to be a positive value. Although the one exception of it is the absolute value of 0, that is 0. That's the only one that's unsigned. All right, let's go on to some examples. Now, for example 8, we see A here is in 2 parts. So if we do the subtraction here, we're left with 14. And if we do the subtraction here, we're left with a negative 14. And you'll notice that the distance that they are from 0, in this case, is 14 units. And in this case, it's 14 units. Okay. Now let's look at another. And there is a protocol to follow here. So the absolute value of a negative x is equal to the absolute value of x. And again, it's always its positive value. Now, the absolute value of 7 is 7. 7 divided by 7 is 1. Now, the absolute value of a negative 7 is 7. Divided by a negative 7, we use the rule, unlike signs, will be a negative 1. Anything divided by itself except for 0 is a 1. And watching the signs, we get a negative. Now here we're asking for the negative value of a negative 5, the absolute value of a negative 5. Well, this comes out to be the absolute value of a negative 5 is 5, and then we apply that negative sign. So this would be negative 5. Another way of thinking of this sometimes is we put a 1 there. A negative 1 times the absolute value of negative 5, which is 5. Negative 1 times 5 gives you negative 5. Now, items F and G are a tad tricky. So let's look at the explanation they give, that even without a calculator, we know that the square root of 7 is larger than 2. See, square root of 4 is 2. So that we know then that this is positive. So when we take it out of the square absolute value sign, it's this. That's a little tricky. While in case G here, the absolute value of this, when we take it out of it, the negative 19 becomes positive, and the square root of 7 will be, in this case, negative. So noticing what's being done here, a little bit tricky. All right, let's go on. So in summary then of what we've been doing, we see that the absolute value of anything is greater or equal to 0. So this would indicate a positive value. The absolute value of something that is negative is the positive value of that. A is less than or equal to the absolute value of A. And then the absolute value of AB, we could separate it. And again, in its fractional form, you could separate the numerator and denominator, and keeping in mind the restriction that the denominator cannot be equal to 0 here. And in something like this, this is called the triangle inequality, and the reflection of the facts that one side of the triangle is never longer than the sum of the other sides. That's an interesting point. Okay, so in example 9, we're looking at letter A, and here the absolute value are also a grouping symbol. So we do what is inside. -3 times 5 is a -15. The absolute value of a -15 is 15. Okay, and in this case, letter B, we have 1 is equal to a -3 plus 4, which is a 1 here. And then the value here of a -3 is 3. 3 plus 4 is 7. All right, let's raise it up a little. These are illustrating things we talked about earlier. So here we're saying that 7, absolute value of these when they're added together is 7, is less than or equal to the absolute value of 3. A -3 is 3 plus 4 is 7, so that works out. And then here they're just showing that we can separate the two, and the absolute value of a -3 is 3, and we get that. Again, you'll be doing your practice and certify to a quick review now of algebraic expressions. Well, when there are letters included in the mathematical expression, we think of it as algebraic expressions. And terms within an expression are separated by either a positive or a negative. And the letter is the variable part, and what's in front of the letter is the coefficient. And in a sense, it's 2 times x, whatever the value of x is. So these are factors within a term. All right, quick on that. We're almost. Now, as we go to example 10 here, we're looking at this algebraic expression. Well, because of the parentheses, this is all one term. This is one term. And this is one term. So here we have a factor that will be multiplied by this. This is a 5 that's multiplied by that. And then this is just what we call a constant. Okay, now they're going to give you some other examples, but I think we can pass. For example 11, we're going to do some substitution here for A, and it's done this way. 5, put a parenthesis, what their x value is 4 to the third power. Well, they have it worked out down below. So we do and then there's a minus 16. So 4 to the third is 64 times 5 is 320. Minus 16 gives you this. And then here, again, kind of complex, but being able to substitute carefully, and we'll pause to do that for you. And the use of parentheses, very helpful. So I've copied it and substituted where I could. So a negative 2 squared becomes a positive 4. Negative 3 times 4 gives me a negative 12. Now I do what's in the parentheses first. This is going to end up as a 1. So negative 2 times 1 is negative 2. That adds up to a negative 14. And as I mentioned earlier, this is like a whole beginning algebra course all put into one lesson as a general review. And here are some properties of algebra. So again, include what you can here. Closure, that a plus b is a real number, and a times b is a real number. The commutative property, a plus b equals b plus a, and in multiplication is ab equals ba. The associative property, here we have the same order, but we're grouping them differently. This applies to multiplication also. Now, the identity property of addition is we can add 0 to anything, and it's still the same. And the multiplicative property of the identity is we can multiply anything by 1, and it doesn't change its value. Now, the inverse of addition is what we would add to it to make it a 0. And here we're multiplying the reciprocal of something so that the product is 1. And then the distributive property we'll use a little bit later when we do factoring. And this, from left to right here, that's distribution. If we go from right to left, that's factoring. All right, a quick review. Now, reviewing these background items in example 14. This is a simple equation. Y plus 12 equals 18. If we want to isolate the y, what do we add to a 12 to make it a 0? Well, it's additive inverse, so negative 12 to this side, negative 12 to that side, and we get y equals 6. Now here, when we see a negative 6x equals 30, we can think of solving this in two ways. We could use the reciprocal to get a 1 here, which is what they're doing, or you can just divide by a negative 6. So here x equals a negative 5. Okay, we'll raise it up a little. Now in doing letter C, we're going to use what is called the zero factor property to solve a quadratic equation. Now, if x is 0, this side would become 0. And they're suggesting that we multiply both sides by 0 here. And whereas 0 equals 0, that is true, but there's something wrong with that. First of all, this is a quadratic equation. We're only getting one answer. So again, reviewing, we would put this in standard form, x squared minus x minus, bringing the 2 over, changes its sign. And then now we factor that. And we get x, 2, 1. And we need a negative here and a positive there when we FOIL this to get this. Now the zero factor property is if the equation is in standard form, we factor it and then we equate each of the factors to 0. So here x would equal, transposing that, a negative 1, and here x would equal 2 would be the solution for that. And they are actually describing that down in section D. So again, background and review. This then brings us back to our original and completes this lesson, which in a normal introductory algebra class may take 4, 5, or 6 weeks to do, and we did it in less than an hour. So good luck and bring questions in.